few months ago I bought this very nice but quite expensive Stirling engine model as a demonstration tool for my Stirling Engine Bike project. But I have a problem. I don't have an easy way of running this engine because it requires a temperature difference between the top and bottom plates. I can use a hot cup of water, which makes it run really fast for a short period of time. Or I can use the sun to heat up the top side, which should allow it to spin all day long. But I live in the UK and the sun rarely appears. I even resorted to using my 3D printer heated bed to power it. But this just seems a bit ridiculous. I just want it to be able to run on my desk all day long with an easy source of power. And my solution is ice. Now of course ice isn't a power source, but by placing the engine on top of a block of ice can keep the bottom plate cool, allowing the surrounding air to heat up the top side, essentially turning the air into a power source to melt the ice. Though I don't want a puddle of water on my desk, so I 3D printed this small stand for the engine, which I can place 4 ice cubes inside, and this cools the underside of the engine just enough for it to run. And because the stand is designed with hollow cavities inside for insulation, the ice keeps the engine running for a surprisingly long time. And whilst this could be the end of the video, I couldn't give up here. So let's over-engineer this. To set a control time for how long the ice will run the engine for, I need to control the ambient air temperature around the engine, because this basically dictates how hot the top plate will get and how long the ice will stay ice for. So I need to put the engine and the stand inside of a temperature controlled chamber, which I don't currently have. But I do have the next best option, a Prusa Core 1 3D printer. By placing a bit of cardboard on top of the heated bed to insulate the engine from being heated directly, and the chamber ventilation fans set to keep the temperature at 25 degrees Celsius, we now have an actively temperature controlled chamber to run some tests. And with 4 ice cubes placed inside of the ice tray, it's time to get a control runtime, which if I'm honest is way longer than I was expecting, and I'm starting to question if I'm going too deep into a silly experiment, because at 3 hours and 22 minutes of runtime from 4 tiny ice cubes, surely we don't need more. Of course we do. I then thought I'd freeze the whole tray as one large block of ice, as this would increase the amount of ice whilst also reducing the surface area, hopefully prolonging the melt time, which considering the amount of ice has been increased from 74 grams to 130 grams, it wasn't a shock that the runtime is now far longer. How long to be exact? 6 hours and 17 minutes, almost doubling the previous time. I then did some calculations to work out how much energy is required to melt 130 grams of ice, which is about 43 kilojoules or 12 watt hours. This means over the 6 hours of runtime, we can pretend that the power consumption was about 2 watts, which seems quite a lot for such a small, efficient, smooth running engine. So maybe there's a bunch of power being lost through the insulation of the 3D print. To check how much energy it was losing through the sides of the print, I designed another ice tray with no insulation and filled it with the same 130 grams of ice, to see if the runtime was shorter. I then noticed droplets forming on the outside of the tray, and initially assumed it was condensation due to the outside of the tray being so cold. But watching the time lapse, it almost looks like the water is leaking through the 3D print, and the condensation height seems to be dropping. After 3 hours and 45 minutes, the engine stopped, roughly 2.5 hours short of the insulated test, which proves the insulation cavities in the 3D print makes a huge difference. But what about the potential leak? Well, I 3D printed some test cups with different thickness walls and filled them with water, and after several hours they were still dry on the outside. And considering the wall thickness of these test cups were much thinner than the non-insulated tray, we can confidently say that the water droplets were just condensation. But this also gives me a good idea for how thin walls we can get away with and still be watertight. And with thinner walls means larger air gaps for better insulation. Now of course, I could go way over the top with this thing and just make it huge, with loads of insulation and a large ice block. But good engineering requires constraints, so I'm going to set a rule that it can't be larger than 120mm in diameter and can't be taller than 40mm, which is roughly the same size as the first ice tray. I then thought I should run a test to see what the absolute minimum temperature difference between both engine plates is required for the engine to still run, and did this by placing a temperature sensor on both the top and bottom sides of the engine. Then by heating the bottom of the engine with the printer bed, I can get the engine to run, which seemed to work surprisingly well with just 10 degrees of difference. And the absolute minimum for the engine to run was around 6.5 degrees. This means that if we're working with ice, there's a temperature difference of about 25 degrees, which is far higher than we need, and maybe it's wasting energy. I originally thought this project would require some custom CNC heatsinks with thermal pads to effectively conduct heat away from the engine into the ice, but it actually seems like it needs the opposite, because the ice is almost too cold for the engine, at least if we're aiming to prolong the runtime. I then ran another test with the chamber at 25 degrees and some cold water in the tray instead of ice, and measured both the water temperature and the bottom plate of the engine, which should give us an idea of what happens after the ice block melts. And apart from my thermometer turning off every few minutes, the engine kept running until the water temperature was about 9 degrees, or 16 degrees lower than ambient air. I then thought if the engine will run off of just cold water, why don't we insulate the ice completely from the engine and just let the engine run off of the water that drips off of the melted ice? So I came up with this design where the block of ice sits on the grille and is insulated from the engine with this removable top plate. Then as the ice melts, the water should cool the air in the side cavities, which allows heat to be absorbed from the engine. The only issue is I can't directly freeze a block of ice in this section as the water will flow down through the grille. So I 3D printed a flexible TPU mould for the ice block, which seemed like a good idea at the time, but the expansion of the ice caused the underside to bulge, and it was a real struggle to get the ice out. I probably could have added a small taper to the walls, but even so, I don't want to have to deal with ice moulds and getting water everywhere when trying to run the engine on a day-to-day basis. So I designed a new version which essentially works in the same way, but this section is an upside down cup that also acts as an ice mould. So I can use it to freeze the ice, and these pegs will keep the ice suspended when mounted upside down inside the tray, allowing the water to drip down and hopefully cool the air in the side cavities. Now I didn't get to test all of these prototypes because it takes about a day every time I want to test the design, because it takes a few hours to print the designs, then it takes a few hours to freeze the ice, and then it takes another few hours to run the tests. And I'm glad I didn't test them all because my engineering ideas were going in completely the wrong direction. With a runtime of just 4 hours and 51 minutes, it's worse than the first tray design by over an hour. Okay, I think what's going on is I'm focusing too much on how the air conducts heat away from the engine into the water and the ice, which is not very effective because air has very low thermal conductivity. But I wanted this because I wanted to limit how cold the bottom of the engine got, so I was using this air gap almost like an insulator to make the engine run slower. But what I completely overlooked was how conductive the PLA plastic is in the 3D print. I was assuming with the first tray that the heat from the engine was being conducted into the ice through the air, but the conductivity of air is about 17% of the conductivity of PLA printer filament. So I now think a large portion of the heat from the engine is probably being conducted through the sidewalls of the tray. This means that with the latest design, most of the heat from the engine that should be heating the water through this air cavity is probably just directly heating the top side of the ice cup. And maybe once the ice melts enough to separate from the pegs, the bottom plate of the engine can't stay cool and it stops running. This is just a theory, but it makes some sense, and maybe if I'm overcomplicating the theory, I'm definitely overcomplicating the design. So let's go back to basics. We need a large block of ice with good insulation, and remember that air insulates far better than plastic. So here is version 5. It still uses a cup design to act as the ice mould, but it simply rests on these tiny fins to minimise contact area for heat to conduct through. This means there is a large air cavity surrounding the whole cup, as well as some extra cavities within the sidewalls. And the engine should be able to rest on top of the cup, hopefully allowing some heat to conduct down into the ice through the sidewalls, as well as through the air. So I placed the tray inside of the printer, loaded in the ice cup, and positioned the Stirling engine on top. With the engine running, I started the stopwatch, hoping that this would set a new personal record, which it was definitely off to a strong start. And at just over 2 hours in, my thermal camera was showing that the outside temperature of the print was around 17 degrees, which was a good sign that the installation was working, with the upper portion of the tray at a lower temperature right at the engine base. But this was the point where I started to get nervous, as I had to go out and hope that the engine would still be running when I got back. But then my camera battery died, just before the 6-hour mark. Fortunately, I set up a webcam just in case, as I had a rough idea of how long my camera battery would last from the previous tests. And I honestly couldn't make this up. It stopped at 6 hours and 18 minutes. Exactly 1 minute after the solid frozen block in the first tray design. I don't know what kind of coincidence caused this, and I'm both slightly disappointed and slightly amazed at this result. And I'm starting to wonder if I should have just quit this project at the beginning. Thank you very much for watching.